Okay, good morning everyone. So I'm going to tell you about the results that we have obtained in the effects of the communication networks in power systems. First of all, as I told you before, we are focusing in a very specific problem of the smart grids networks. And this is the dispatch of distributed generators. What is dispatch? Dispatch is that we have a central controller that has to tell to each of the distributed generators the amount of power that each generator has to produce. We use a replicator dynamic algorithm that is a very useful algorithm that can solve this kind of optimization problems. So our results are we have two kinds of results. First of all, we have the analysis using a simulation tool that we have developed of packet dropouts and delays in the smart grid architecture. And we also made a focus on the delays, and we have some mathematical analysis, and we obtained a very interesting result of the replicator dynamics approach for this kind of problems. First of all, our simulation, we use the simulation tool in order to see the effects of the communication networks. This is what happened with the replicator dynamics algorithm when there are not communication effects. We can see that we have a demand profile. The objective is to supply, to cover all this kind of this demand power. And we can see here that the covered demand the demand power is covered in 100%. So this algorithm works correctly with this kind of problems. However, when we have the inclusion of the packet dropouts of the communication infrastructure, we have some problems. Here we use the simulation, and we use the communication architecture that consists of the data transmissions between the microgrid center controller and each distributed generator is made each 15 minutes. And this data communication lasts 10 seconds. So here we can see that when there are packet dropouts, when there are some data packets that are lost, we can see that this is what we want to produce, a flat line, 100% of covered demand, and this is what we get. We get that there are a lot of oscillations in the covered demand, and we can see that for example, here we have some overproduction of energy, and here we have less production of energy, which is not good for the energy supply, because this has a lot of cost problems, and without for the customer, for example here they are not going to receive the energy that they need. Now we have also made some simulation using the delays. We have a very similar result here, and we have that with delays there are a lot of problems, a lot of issues. Here, like this one, we have those peaks. That means that the energy that the generators are producing are higher than the energy that they must produce. So we can see this on simulations. We have developed a lot of simulations, but we wanted to obtain a mathematical result that tell me why this happened. So we use some very powerful mathematical analysis, and we obtained this result that the replicator dynamics is delay independent. And this is a very important result, not only for this kind of problems, but also for other problems or other applications that can be solved using the replicator dynamics approach. So we have this question. So why does it happen? Why does happen if we have the replicator dynamics and we prove that the replicator dynamics is delay independent? And we realized that that happened because of this. We have the 15 minutes communication, and each 15 minutes the communication between the controller and each distributed generator lasts 10 seconds. We can see it here that when the time delays increases, the convergence time for the algorithm also increases. So we can see here that, for example, at 10 seconds, there are the replicator dynamics for some delays have not achieved the steady state, the convergence time increase. So this explains why these kind of issues are produced in this kind of architecture. But so we can conclude a lot of things here. For example, we can conclude that it's necessary to design new control strategies for these kind of power systems. That the strategies that are now proposed have to consider now the effects of the communication networks. But we can also conclude that the communication infrastructure has to be redesigned in order to diminish the effects of the delays and the packet dropouts. And in the future, we can use the observers for delayed systems in order to improve the behavior of the smart grid. So those are the results that we have obtained. And if anyone has any question, it was kind of fast.
I don't understand. Given that the communication is like 10 seconds or something like that, and the replicator dynamics doesn't get into the steady state behavior.
Yeah.
That is the problem.
Yeah.
But given that the replicator dynamics is a differential equation, why just don't solve for the steady state and give that out to the microgrid or the
I mean that solve for the problem and then
you can also just solve the
optimization problem.
with the steady state equations.
Yeah.
Why you
the problem is that when we consider some dynamics, for example, maybe some generator can be turned on or turned off, and that becomes a grid system, and then the dynamics of the system changes as you told us in your presentation last time. So that kind of dynamics cannot be solved using, for example, the steady state of the system. So we need to consider that those uncertainties may occur. So that's why we use that. Another question.
This is good.